Good evening, you all. We are now at the third session of day 2. I welcome you all to CIT Quantum Hackathon workshop series as a part of Qiskit Fall Fest sponsored by IBM Quantum and Qiskit. I take this privilege to welcome Mr. Alain Chance, founder and CEO AlainQuant LLC and QuantAlain SASU. Alain Chance is a co-author of a book, Quantum Chemistry and Computing for the Curious, illustrated by Python and Qiskit code. Qiskit advocate and IBM certificated associated developer quantum computation using QAKT at VO 2x since 2021 and completed a number of hackathons pertaining to quantum computing series since 2018. He is also a mentor for Qiskit Global Summer School 2022 and Qiskit Quantum Explorers Learning Program August 2022 to Feb 2023. Congratulations on your achievements, and it is quite an inspirational journey, sir. So now we are ready and waiting to hear about simulating interferometric sensing of quantum superposition of enantiomer states with Qiskit code. From you, sir.
Oh, thank you for having me. It's my pleasure to deliver this talk. Don't be afraid by the title. It's not going to be a lecture on quantum chemistry. It's my purpose is to illustrate with a use case, a toy use case, what we can achieve with qubits, a couple of quantum gates, and illustrate the concepts of superposition and entanglement, I would say, in a fun environment. So, as a starter, I'd say that this Jupyter notebook, I've tested it. It works locally. This is the one I present now under Ubuntu in Windows. It works also in the IBM Quantum Lab, and I've also tested it with Google Colab. And I will share this with all of you, all the participants. It's an MIT license. Some code actually comes from the so-called cut-down companion, Jupyter Notebook, of the book I've written, and which means you can reuse the code very easily. So, okay, so let's start. There is a bunch of statements. I hope most of you are familiar with Python. If not, don't worry. It's very easy to follow. So there is, first of all, in order for this Jupyter workbook to work in all environments, I've included everything which is needed. Everything is contained in this Jupyter notebook, and you don't need any skill to make it work. So, for instance, we install NumPy, which is a well-known library, just with these commands. So Qiskit, visualizations, some Qiskit utils. Qtip, actually, we don't use it in this notebook. It's for displaying a so-called block sphere. PySCF, ASE, PubChemPy. We shall see further down the way it is done, but and then we have got the corresponding import statements. So basically what I'm going to do is just execute all cells above, okay? And now I'm going to demystify what is an enantiomer. It's very simply, in chemistry, when we have molecules or ions that are mirror image of one another, by definition, they are called enantiomers or optical isomers. In addition, if these images are non-superimposable, for instance, your left hand and your right hand cannot be superimposed. You cannot rotate or your right hand to make it fit with your left hand. They are mirror one another and are not superimposable. In that case, it's called chiral molecules. And the important thing is that they differ in their ability to rotate plane polarized light either to the left or to the right. So I won't go into details about the conventions which are used to identify the different enantiomers. There are two of them. I think the interesting thing is to find an example. So this is what I found. I did a search on the internet, and one is called Alain, and there is the one which is depicted on the left, which is occurs naturally. Nature, at least on Earth, we see that. And on the right hand side, you have got the enantiomer, which is the mirror image, which we do not see naturally. Now, at first look, it appears that the NH3 group is position. You don't. We see that the H3C is positioned differently, but this is a flat image, two-dimensional. Not really the first time I encountered this. I wanted more. So what I did is there is a free and publicly available resource of high quality, which contains the descriptions of substances and their associated biological activity information, and also, interestingly, 3D record information about the positions of atoms that make up a molecule in 3D. So what I did is I wrote a small piece of Python that uses a free available package known as pubchem Py for Python, and extract the record given the molecule name, and then we assign different colors to each atom which makes up the molecule, and then we plot it with matplotlib, which is the I would say the de facto standard when you want to plot things with Python, and another one which I discovered, which allows manipulating. So it's a very simple piece of code. Let's execute this. And now I'm going to show you a 3D view. Okay. So this is what we get with matplotlib. So I've depicted the carbon atoms in dark gray or black, the oxygen atoms in red, the nitrogen atom in blue, and the hydrogen atoms in yellow. But this is static, not really nice. And the other one is much more fun to use because I can rotate. You see, I can see the different positions of the atoms. Okay. But there is even better. In my book, and this is illustrated here as well, we have a 3D viewer which comes with the ASC package. So I'm going to execute this. And this is what we get. And again, which is interesting is you can rotate things, because at first we couldn't see the hydrogen atom there, but now we can see it. And we can compare with one illustration which comes from the US Department of Health and Human Services, NIH, and we see it's really consistent. So now we have got a three-dimensional view of the naturally occurring alanine. And now what's interesting is let's have a look at the enantiomer. So same thing. Okay. And again, I can rotate and see the relative positions of the atoms that make up the molecule. And again, let's have a look, a 3D view. Okay. And again, yeah. And now it's interesting to try and see the difference between this one and what we had up there a few seconds ago. And you see the difference is the position of this hydrogen atom and the this CH3 group between this. So if you have got visual memory, now we jump to this, and you see it's different. Earlier above we had the hydrogen atom here, and this was stuck here. So yeah, I mean we can see the difference between the two enantiomers with this 3D depiction. Something interesting which struck me at first, and I'm not a an expert in chemistry. I'm just curious, right? I noticed that the hydrogen atom is stuck to one of the oxygen atoms when in the 2D description, there's no such thing. Then I asked someone in my team who really is an expert in chemistry, and she told me, but this depiction is correct, but it is unstable. What happens is that one of the hydrogen atoms will move from there to there, and then it becomes really more stable. Anyway, so my point there is to share with you my curiosity. I didn't want to. I couldn't accept this as the final depiction. I wanted to experiment, and this is what I've done with Python. Okay. Um, Now you may ask me, but Alain, what's the relationship with Qiskit and quantum circuits, all that stuff? Well, this is where the excitement comes in. I stumbled across a paper when writing my book, and it is documented in my book, but not as detailed as I'm sharing with you now. There is a team of researchers who have proposed an experiment to prepare, guess what, a quantum superposition of left and right-handed states of enantiomers. Now, you know what left and right-handed states. I mean, it means that one enantiomer would polarize the effect of light being shined on a one enantiomer. It would be rotated to the left and the other one to the right. So this is why it's called left and right. But what's exciting is that these researchers mention it's possible to prepare quantum superposition. Okay, and there is a potential application by being able to not just preparing quantum superposition as explained there, but also being able to separate the two different enantiomers. Then this could be used to measure so-called enantiomer-dependent forces due to nearby surfaces, or chiral molecules or optical fields with unprecedented accuracy. This is very important in quantum chemistry. We need to have very accurate measurements. Okay, so it's not my purpose to dive into the details. I don't want to go into the rabbit hole, but this was source of inspiration for what follows. So the what I'm going to introduce now is, and I know you have been, I mean, some speakers before me and presumably after me will present you the qubits and quantum gates, but let's review what that means. Okay, so by definition, a qubit, quantum bit, it's a quantum unit of information. It represents, by definition, a two-level quantum system. And so that's the physical description, if you want. And mathematically, it lives in a so-called two-dimensional Hilbert space. We will understand what that means later on. And so the space where this qubit lives, it's two-dimensional, and these are the so-called Dirac notation. This is a ket 0, and by definition, it's the same as vector 1 0, and 1 is 0 1. So this is the basis. These are the computational basis states of the quantum space where the qubits live. And any single qubit state can be described by linear superposition of the computational basis with complex coefficients. So this is the way it is written. Okay, and so it's linear is really essential in quantum physics. The except for measurement in quantum physics, every operator, every action on states is linear. So if you have got a valid state or two valid states, any linear combination of them is also a valid state. And the trick is these are actually complex numbers. And there is a normalization condition. So if you well, take the modulus squared of each coefficient and you add them, it must be equal to 1. Okay. So what's important is that a qubit, during the execution of any algorithm, quantum algorithm, a qubit is effectively in a quantum superposition. But as soon as this is measured in a computational basis, it will be found in either of those two states. And the probability is the modulus of the complex coefficient square. Okay. And don't ask me why. This is the way we teach quantum physics ever since it was invented. It turns out it works. Okay, and if we have more than one qubit in the system, then the state is described by a vector, but this time it's in a 2 to the n dimensional Hilbert space. And it's formed by taking the tensor product of the Hilbert spaces of individual qubits. For example, for 10 qubits, we have got a vector in a 2 to the 10, which is 1024 dimension Hilbert space. Well, you don't need to understand everything now if this is new to you, but this is important to bear in mind that when we obtain results, and we will have examples down there. If you want to figure out, hey, if I measure the state, then what matters is that you know that by taking the square of the modulus of the coefficient, which applies to the basis states, then you have got the probability that it will be measured. Okay. Now, something which is a bit annoying, but such is life. When I learned quantum physics, that was back in 1980s. Actually, I got my degree of École des Mines in Saint-Étienne in 1981, the same year as Alain Aspect did his famous experiment at Institut d'Optique, Université Paris Saclay. And at that time, it was not so much fun to learn quantum physics. It was, the mentality was shut up and calculate. Now it's much more fun because we have got actual quantum computers and frameworks like development frameworks like Qiskit. Now the thing is, the way I was taught quantum physics, I used the so-called physics standard convention for the ordering of qubits in a tensor product. So these are really equivalent ways of writing the same thing. This is a tensor product of n qubits, and this is an equivalent lazy way of writing the same thing, and this is the same thing. Now, Qiskit, and that makes perfect sense for computing, uses a different ordering. It's just the opposite. So it's very similar to what you find in base 10 or base 2. In base 10, when you say 1024, 4 is the digit with the least weight, and 1 in 1024 has got 10 to the 10 to the power of 4, right? 1000. And it's the same here. Now, the thing is, so when you read books and sometimes even Qiskit documentation. Sometimes you see the familiar physics convention, and sometimes you see the Qiskit ordering. So I'll give you another example. If qubit 0 is instead get 0, 1, 0, and 2 instead in state 1, in many physics textbooks, this would be depicted as 001, whereas in Qiskit is 100. Okay? Now, for single qubit operations, you won't see any difference, but as soon as you have got 2 or more qubit operations represented by matrices, then it makes it appear very different. So we will only review 3 quantum gates that I will use later on. So by definition, a single qubit quantum gate has got a equivalent matrix, which is a 2 by 2. And maybe this is the first time you see this. It is the dagger symbol. So it simply means that if you take the conjugate transpose of the matrix and you multiply it by the matrix, you get 1, and you can do this in different. So it's called a unitary matrix. It's important because it means that any transformation which is done on a qubit preserves the norm, the length. So I mentioned earlier on that a key convention and constraint is that the length, the norm of the vector is 1, unit 1. And unitary, all quantum gates are unitary. They preserve the length of the qubit on which they operate. Now let's dive into very exciting examples. So the first one is called the X gate or the NOT gate. It's very simple. It maps gate 0 to gate 1 and conversely. So it's really equivalent to or similar to the NOT gate in classical computing, which changes a 0 to a 1 and a 1 to a 0. So let's see how this is depicted. So when you see such a matrix, in the first column, you have got the effectively the mapping of 0, which is the first qubit, the first state of the qubit in the computational basis state, and you see that you see 0 is represented by vector 1 0, and when the matrix X 0 is mapped to 1, which is 1 0. Okay, 1 is 1 0. Okay, and the same here. So it's the, I would say, the simplest quantum gate you could think of. Okay, now a gate which has no equivalent in classical computing, it's called the H or Hadamard gate, and it maps the basis state gate 0 to the sum of the two, and there is a normalizing coefficient 1 over square root of 2. Okay, and it's also written as ket plus. Okay, and the basis state ket 1 is mapped to 0 minus 1, again with a normalizing factor of 1 over square root of 2, which is written as ket minus. Now, if you measure the state plus or the state minus in the computational basis state, then you will have an equal probability of measuring either 0 or 1. So this is the gate which enables us to create superposition of states. It's represented this way. And again, so another way to look at this matrix is to see that if you have got 0, the 0 state, it's mapped to 0 plus 1, and you have the normalization coefficient of 1 over square root of 2. And the same for 1. Okay, this is the column for 1. And you have got 1 and -1. Okay. Now it's important you get comfortable with understanding from reading the matrix. You can work out what would be the effect, the mapping of the gate on any BC state. Now these were so-called single qubit quantum gates because they operate on just one qubit. But there are also 2-qubit gates. There are also 3-qubit gates, but we won't cover that today. So this is a very useful one. It's called a controlled NOT. It's written C0 or CX. It's a gate. It operates on 2 qubits. So the definition is very simple, actually. If the first qubit is in state 1, then it performs the Pauli X, which is the same as the X gate, the NOT operation, on a second qubit. Otherwise, it leaves it unchanged. Now, with the tensor ordering of qubits, which is used in most physics textbooks, and the one, by the way, which I'm most familiar with, this is the way it is depicted. Okay, so you see that if the so it's 0, 0, 0, 1, 1, 0, 1, 1. If you have got 1, 0, and 1 is the leftmost qubit, then it is 1. Then it means it performs a NOT on the other one, which means we end up with the state 1, 1, which is represented there. Okay. But with Qiskit tensor ordering qubits, it looks completely different. Now, I've got something for you which should help you out. I've written a small piece of code which uses the so-called unitary simulator of Qiskit, so that we can check this result. Okay, so this is the quantum circuit. So let me explain a bit. So here this is really Qiskit code, and here we use the quantum register class to create a register of 2 qubits. Okay, and here we actually use the quantum circuit class to create an instance of a quantum circuit QC, right? Now, then we perform a control NOT, a CX, on qubit 1 using qubit 0 as control qubit. Okay, and I use this to display with a nice look the quantum circuit. Then select the unitary simulator. I execute the job. I get the result, and then I get the unitary matrix from the result. Let's execute and see what's going on. Okay, so there we are. So the first display was the quantum circuit. So this is the way we depict a control NOT. Okay, so the little dot pertains to the control, the qubit which is in control, and the plus is the target qubit. And you see the matrix is exactly what I told you it is. So this is a simple way to make Qiskit work and find out the way the matrix looks like for any given quantum circuit. It needs not be restricted to a single gate. Okay, so but this is rather, I wouldn't say boring, but it's the but this is to be used as a reference. I would say now the fun really starts. Or at least I enjoyed preparing this material, and I hope you will enjoy it as well. So we introduced earlier on the concept of interferometer, and I mentioned that some team of researchers have performed or thought about an experiment putting enantiomers in superposition of left and right states, and then doing some interferometry to sort out the different enantiomers. Okay, now this is the basis of this, I would say, series of quantum circuits. Okay, it's really a toy use case. It's not meant to be representing something of value, but I think it's very interesting. So the first thing, when you think about using quantum computing for any given topic, is to think about how you are going to encode the information. In our case, we have got an enantiomer, which has two, I would say, properties of interest. One is the handedness, is it left or right? And the other one is the direction of propagation. Okay, and so we need 2 qubits to represent this. And now I'm going to introduce the way we have I have done the encoding. So for the so-called handedness, which means is it left or right? So if it is left, I use ket 0, and if it is right, I use ket 1. But what we have seen above, we can do more. We can easily map a superposition of left and right-handed with the states I've told you about earlier on. And this is where you see the power of qubits as compared to ordinary bits. With ordinary bits of information, we would have needed more than 2 bits, right? But more than one bit 0, 1. But with 1 qubit, which is in either state 0 or 1, or any linear superposition of these two states, we can easily map the superposition left and right handed state to this state of qubit 0. Okay. Now, so for direction of propagation, I only need horizontal or vertical. So it's the same trick, basically. Oops, there is a typo. Actually, it's state Q1. So I will fix it. Okay. Now, this might help you understand what we mean by computational basis state. So we have got as basis, we have got actually 4 combination, four states. Okay, 0, 0, 0, 1, 1, 0, 1, 1. And I've explained what it means. So again, this is the Qiskit tensor ordering of qubit. So this is Q0 and this is Q1. Okay. Right. So this will be useful for later on. Okay. I will move on, and I guess we will have plenty of time afterwards for questions and answers, because I might give answers to questions you might want to ask later on. For comfort, I've defined a function which I call show, which displays the drawing of a quantum circuit and a state of a state vector using LaTeX, so that it's rendered very beautifully. So it's very simple. Okay, that will be handy. Now, I use ideas which actually come from linear optics, but transposed to the use case of enantiomers. In the literature, you will find that we can simulate a mirror with the Pauli sigma x is really the same as the X gate, so it's the NOT gate. Okay, so that makes sense, because if you have got this, if you apply the X gate, the NOT gate to get 0 horizontal, you get the vertical, and you get if you apply a mirror, it's exactly the definition of enantiomer and handedness. If you apply the NOT gate to ket 0, you get ket 1. So you invert left and right, which is exactly what you would do with a mirror. So it's a very simple mapping, right, to model the action of a mirror with the X gate. So I think this is pretty obvious. Now, this is what you find in literature. A beam splitter is represented by this matrix. And by convention, it's not me who invented the convention, but don't worry, there is a phase shift of pi/2, which is assigned to reflection. Okay. So what we have seen above is from a quantum circuit, or which can be reduced to a gate, a single gate, we can gate the matrix. We can do the converse. So what I'm going to do with this piece of code is I'm going to create a gate which is called beam splitter, BS for beam splitter, from the definition. Okay, this is exactly the same as this. Okay, in Python. And now we are going to make some experiments. So we suppose we have an enantiomer moving horizontally. Okay, and we are going to see what happens when we put the beam splitter in a quantum circuit. So let's have a look. So it's just one qubit, Q1, which is the direction of propagation. So it's the state vector is 1, 0, which means it is in a state ket 0, right? Because this is ket 0, this is ket 1. And when you apply the beam splitter, we get this, which is 1 over square root of 2, 1, and I, which is I square equals minus 1, 1. So this is the way we interpret this. So the enantiomer moving horizontally, yes, it is moving horizontally because it is in the 0 state, represented by, yes, Q1 equals ket 0. It has been put by the beam splitter in the state which is a superposition of the states moving horizontally, okay, and moving vertically, but with a phase shift of pi/2, okay. And we can do the same with the enantiomer moving vertically. This time, in order to say we move vertically, I applied a NOT gate. So initially it was moving horizontally, but with the NOT gate, we simulate moving vertically, and then we apply the beam splitter, and we have got a very similar result. Okay. So this was just an appetizer, because now we're going to do the real, I would say, simulation interesting. So again, from an interesting source, but which pertains to optical linear optics and the Mach-Zehnder interferometer, I found out a good way to represent a polarizing beam splitter is using this matrix. And unlike the beam splitter we have just seen, there is no phase change or reflection. Okay, so we can create a polarizing beam splitter gate named PBS, just the same, using this matrix. Okay. Now you might have noticed something. I hope you do, because we have seen this matrix before, haven't we? Yeah, I think so. Let's have a look further above. I'm sure we have seen it. Yes. So you know what? Hey, this is the same as the control NOT gate. So what's fun is that the author of this paper, who it's not a paper about quantum computing, did not realize that this complicated looking matrix is actually, when you look at it from a quantum computing standpoint, it's very simple. It's just a control NOT gate, right? Using Qiskit tensor ordering of qubits. So now we have got the polarizing beam splitter. We can make experiments. So the first one, we consider the case of an enantiomer moving horizontally and in the left-handed state. So it's very simple. 2 qubits, and they are both in state ket 0. So this is there in the state vector, because this is 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 is represented by this state vector. We append a polarizing beam splitter and we see what's going on. Well, nothing happened. It does not change. The state at the end is the same as before. So this is the way we interpret this: the enantiomer moving horizontally and in the left-handed state, represented by this pair of qubits, state 0, 0, using Qiskit tensor ordering of qubits, has been transmitted in the horizontal direction propagation by the polarizing beam splitter. Okay, so the polarizing beam splitter, as advertised before, transmits left-handed 100 states. Nothing happens. Okay, now let's see what happens if the enantiomer is still moving horizontally, but this time in a right-handed state. Let's have a look. Now, in order to have the right-handed state, we use the mirror, which is simulated with the X gate, right? And so we have got this state, which is the 1, 0. And so 0 is the handedness qubit. So it's 1 for right-handed. You see, it's even for me, it's difficult exercise because I'm so used to the other convention, right? But then we add the polarizing beam splitter and see what happens. Ah, that's interesting. This time we are in this state. So the enantiomer moving horizontally, okay, this is 0, and in the right-handed state, okay, represented by this state. This time it has been reflected in a vertical direction of propagation, which is represented by this, okay. So, yep. So again, I mean, this is as advertised from the very beginning by the definition of this polarizing beam splitter. It reflects right-handed states, okay. So far we only confirmed what was the definition, basically. Now we are going to do something more ambitious. This time we are going to simulate the action of polarizing beam splitter on an enantiomer moving horizontally, but this time in a superposition of left and right-hand states, left and right-handed states, which is the simulation inspired by the experiment I mentioned above. So let's see. So this is the code. So this time I use the Hadamard gate, the H gate, to put the enantiomer in a superposition of left and right-handed states. Okay, so this is the what happens. This is what it looks like on the state vector when we apply the Hadamard gate to just the qubit 0. This is the way it looks. And then when I put the polarizing beam splitter, something interesting happens. This is the final state. Now this is the interpretation. So again, we start with an enantiomer moving horizontally and in a superposition of the left and right hand states. So it is represented by this 2-qubit state. I've factored it, and this is something, this symbol means tensor product. So this is exactly 1 over square root of 2, 0, 0, 1 over square root of 2, 0, 1, and it can be factored this way because it's the distribution property of the tensor product over the sum. Okay, but what's interesting is the final state is this one. Okay, it's called a Bell state, and Bell is not something that rings. It's the name from Bell, who was the first to put forward this experiment that was later implemented by Alain Chance, that makes it possible to test which interpretation of quantum physics is correct. So there are actually 4 Bell states. But what's interesting is we end up in this so-called Bell state, which is a superposition of left-handed moving horizontally and right-handed moving vertically. And this is of interest because it means that by putting a detector measuring either on the horizontal axis or the right on the horizontal axis or the vertical one, if your measurement gives something, then you know by construction you know that you're dealing with either left-handed or right-handed state. So effectively, you manage to separate the two kinds of enantiomers. And it is also a very good example. This maybe the first example you can see of so-called entanglement. Again, this is the three physicists who got the 2022 Nobel Prize worked on entanglement. And this is something which is weird, which has no equivalent in the classical world where we live, because you can think of until you have made a measurement, if you're dealing with a beam of enantiomers, then you can think of, oh, there is one which is in the left-handed state, the other one in right-handed. We don't know which one, but okay. But actually, quantum physics tells us that if you have got a single, just one enantiomer, it could be put into a superposition of states. And it's not until you make a measurement that nature decides, hey, I'm left or I'm right. This is the outcome, the conclusion from the experiment from Alain aspect. What's interesting with this is that even if we are dealing with such superposition of states, we can still manipulate these states. And this is a simulation with Qiskit. So this is where you see the power of quantum circuits. And here we're using the Qiskit framework to properly simulate actions which are counterintuitive. It's mind-boggling to think that we can actually make computations before making a measurement. When you discover quantum physics for the first time, you think, oh yeah, but I mean, it's only when we measure something that it becomes real, right? But no, because otherwise we would not be able to leverage the weirdness of quantum physics, superposition and entanglement. We can actually manipulate those states. Okay, so and of course you would say, but Alain, I've seen that before. And yes, earlier on I mentioned that the polarizing beam splitter matrix, it's actually the same as the control X, the control NOT gate. So if we do this circuit, we get exactly the same result. Okay. So this is the way you might have been introduced to Bell states. And so, yeah, it's just for the purpose of this talk, I've used the polarizing beam splitter gate, but actually it's the same as the X gate. Now, even more fun, I would say, what would happen if I put yet another PBS, polarizing beam splitter, on the state which has been obtained in the previous experiment? So let's do it. Okay. So this time, well, I start with this state. Okay. I put polarizing beam splitter, and then I put another one and see what happens. Hey, we are back into the original state. So that's interesting. It means that if we put two polarizing beam splitter one after another, well, we reverse, so we can disentangle, if you want, the final state. Okay, so that's it for my talk. I give plenty of references, and also I give there are trademarks. So now there are a few minutes left. I'm open to questions if there are any. Is there any question you would like to ask?
Hello.
Yes.
Sir, actually, I have a question, sir.
Yes, please go ahead.
So it's a general question like I have studied quantum for a as a SEM subject, sir, and I got interested to it. But I don't know which thing to choose, like machine learning or physics, or like that. So, is there anything I can choose as a beginner for studying quantum?
That's a very good question. Um, by the way, I will present my journey in quantum computing. Uh, it will be on the 15th of October, but actually with IST Indian Standard Time, it will be very early on Sunday. Invited by Girls in Quantum. Everyone has got a different quantum journey. In my case, I would say I'm 24 years of age plus 40 years of experience. The first time I was taught quantum physics was back in the late 1970s, early 1980. And what I did is I I used search tools on internet. I was fortunate to be able to attend Qiskit hackathons from the first one organized by IBM Quantum back in 2018. And I learned a lot by attending hackathons, but also I attended online courses, one by Umesh Vazirani, who is one of the pillars of quantum physics and quantum computing, um, organized by Berkeley University online. Um, but there are a bunch of very good books. I guess in the on, Discord there is a channel sharing resources. Um, for practical purposes, I recommend there is the so-called Qiskit Pocket Guide. I don't know if you can see. There is a Qiskit Pocket Guide.
Yes, sir, I can
Um,
see it, sir.
yeah, you can see. And of
Uh,
course, there is also my book where I introduce. It's not just me, Dr. Keeper Len Sharkey, my who is lead author, and myself. We introduce in chapter one, the introduction. We introduce the historical perspective of quantum uh, um, physics with a focus on chemistry. And in the appendix of my book, there is a mathematical refresher. I'd say be curious and feel free to ask questions in the Discord channel. There is not a single good path to quantum computing.
okay, sir. Your journey was very inspirational, sir.
Okay. Any other question? I don't know if we're running out of time. I think we have got a few more minutes, haven't we?
Yes, sir.
Don't be shy. I mean, feel free to.
So good evening. Actually, the presentation was pretty clear.
Thank you.
So I have no doubts in it, sir.
Okay, so my recommendation for you all is, and this is the key, in mathematics from a very early, when I was a child, high school student above, I learned mathematics by being my own teacher, basically. So it's interesting to listen to courses made by people, but in order to really understand, you must become your own teacher. So and honestly, when I started to refresh my knowledge of quantum physics and quantum computing, as soon as I understood something, I I put it together in my own course, if you want. Okay, and I encourage you to get hold of my Jupyter notebook, which I will share very soon, and replay the experiments, modify them, uh, change them, and see what's going on. It's the only way to learn efficiently. Um, it is really it seems so simple, but it's by experimenting and being curious. Experiment, try different ways. At first, it takes more effort than just reading stuff, but then it pays off. Um, yeah, it's very important, in my opinion, that you listen, to the bright speakers and read the good books and good papers and good tutorials. And we are lucky nowadays because there's so much good stuff available for free, and we can replay for free, experiments. So there's no excuse. It's really an opportunity to learn by becoming your own teacher, and then once you are sufficiently comfortable, well, like me, you can try and teach and share your knowledge, and that's the ultimate test, because you have got to really understand what you're talking about in order to make it crystal clear. Okay. Anyway,
Yes,
I'm really grateful for this opportunity. It's really my pleasure to do such talks. I hope I will be given more opportunities in the future.
Yes, sir. It is our pleasure to have you, sir.
Thank you. I don't know if there is any more comment or question before I guess we close this call.
So I think we have now arrived at the end of our session, sir. So
Okay. So thank you very much. I will be available via the Discord. You know how to reach me. I also have a profile on LinkedIn. You just search with Google my name and you will find me. So great.
I once again extend my gratitude to you, sir, for joining hands with us.
Thank you. My pleasure.
Yes,
Have a
sir.
great day.
Thank you, sir.
Goodbye from me.
Thank you, sir.